Uh, Sujit Sharan is the Senior Director of Advanced Design and Technology Solutions Department with Assembly and Test Technology Development at Intel. He has over 30 years of experience in semiconductor processing and packaging, having worked for Hampshire Instruments, Micron Technology, and Intel. So welcome, Sujit.
Thank you, Ara. And I hope everybody can see my screen clearly. And we'll just get started right now. I think heterogeneous integration, we'll be hearing a lot about it for the next 3 days. Today, I'm here to talk about the opportunities that are there with heterogeneous integration, the complexities involved, talk a little bit about system technology co-optimization and why it is so important, enabling the ecosystem and other vendors, and then one slide on the next steps. So heterogeneous integration, what are the key elements that we look for in heterogeneous integration? So it basically, from our definition, we would look at heterogeneous integration as combining different chips and chiplets using advanced packaging techniques. These chips and chiplets can include different functionalities, memory, compute, I/O, graphics, across varying silicon nodes and across different foundries. We have looked at heterogeneous integration both from a 2.5D advanced packaging and a 3D advanced packaging perspective. In the case of a 2D advanced packaging, we have looked at what we call embedded bridge architecture, which is something that Intel has been doing for a little bit now, and we have products out in the field with EMIB architectures, where essentially you are connecting two chips together through a very dense fine line space based silicon based bridge, which is embedded actually in the package. So it is part of the package. We drop through bumps, we connect our I/O signals, which need to go across in this case, the high bandwidth memory and the SOC die through the EMIB layers, which is typically consists of 4 to 5 metal layers of embedded on a silicon piece of silicon. We have looked at driving, and we drive both signals and power and ground through the bridge to essentially create a full network across the HBM and the SOC dies. Obviously, it involves doing the die stacking, the embedding the TSVs, the distribution layers, so on and so forth. And it is an interesting challenge, which I'll talk about, is you do have aspects of it where you have to co-optimize across both the chiplet dies as well as the chiplet signals which come out directly to the package. So in this case, the reason we call it 2.5D is you have signals which come out directly to the package from the top tiles, as well as you have what we call the die-to-die interconnects, which goes through the embedded bridge. So not truly 3D, as distinguished where we see the 3D advanced packaging, where all of the top tiles are on top. They could themselves be stacked, but they are all on top of a base die interposer where we connect them with micro bumps, and all signals will either go through die-to-die routing, which is a die-to-die signaling, or they'll come through the base die, spread out to standard package bumps, which are then packaged onto the substrate, which goes onto the motherboard. In this case, in the 3D case, we do not have signals which go directly from the top tile to the package. Everything goes through the base die, as opposed to the case of the EMIB, where the key I/O signals go through the bridge die, but there are other signals which we don't need the dense interconnects that will go straight down to the package bumps. The benefits, I think you will hear a lot about it over the next couple of days. Reuse strategy is very important. We can reuse a lot of elements from both the design as well as the chiplets directly. It is very scalable. You can mix and match. You can have in this instance, you could have the top die 1 and top die 3 remain the same for different package configurations, but change the top die 2 to get different functionalities. You could use silicon, like we talked earlier, from across diverse functional foundries, diverse silicon nodes, and put your more expensive, your compute tiles and your advanced nodes for the really high performance computing, and then use the cheaper nodes and the for the less stringent requirements on some of the other chiplets. So it makes it very easy to manage the cost. Time to market is a big issue. We do believe that this gives us the advantage again of the flexibility of being able to do different configurations and bring different products to the market at the appropriate time. A lot of ease of product optimization and customization. Again, same thing. We can mix, match, drop some of the top tiles out when not needed, again, from both an optimization and a cost play. And then, of course, it does help us manage our manufacturing yield and quality. What are the complexities that arise when we are designing for heterogeneous integration? So as you looked at the previous slide, we have to manage the connectivity across the stack. You have the, in the 2.5D, you have to manage your connectivity both across the EMIB die as well as across the package. In the 3D construction, you have the die-to-die connectivities, which generally the package will not see. You also have to spread out all of your tightly bumped pitch top tiles and into a larger pitch, base die pitch for packaging, which gives us a lot of issues with routing conflicts. How do we manage the base die circuitry so that we can still route along the base die without consuming too much of the area, which is better utilized for the circuitry. RDL optimization, very important. This is essentially to make sure that we are able to very effectively plan our floor plans for both the top tiles and the base die to hit the right pitches required for creating a high yield manufacturing process. In terms of design, visualization of the stack is very important when we are looking at seeing how we are going to address the issues with any, especially when we're in the early planning stages. How do we plan all of our chiplets and our base die or our EMIB dies so that we have the most optimum design? A lot of the bidirectional design data flow, by that I mean is that you have things, layers from the top tile which talk to the base die. You have the base die talking to the substrate. You have the some of the signals passing straight through to the substrate. So a lot of bidirectional design data flow is required to make sure that we optimize the stack correctly. Again, I keep saying optimization, very important, the co-optimization of the stack. And of course, as with anything, there are going to be trade-offs. We look at it from all the perspectives of yield, manufacturability, cost, design efficiency, test, sort. All of these trade-offs have to be managed in a environment where we can do a lot of the what-if analysis. And then finally, of course, we have to validate the whole solution to make sure that what we have designed and are getting ready to manufacture will work as designed. So traditionally, I'm going to just talk a little bit on the EDA tools and how we are using them for our heterogeneous integration. Traditionally, we have had IC design tools really work in isolation without much consideration of package and board. In general, in the past, the silicon was designed, you had the bumps placed on the silicon for a flip chip package. At that point, the package designers would engage, they would take the bump map and design the package around the defined bump map for the monolithic die typically, and also sometimes with an MCP organic package. And the tools were all enabled to do the design analysis and verification of individual components. So silicon folks would run all their tools, they would run their design and they would validate it. They would give it to the package designers who would then run in isolation the package design and run their verification and their analysis, and then it goes on to the board. And that obviously did work at that time, but once we get into the heterogeneous integration era, we do need to design across all the technologies or all the nodes that we are doing. So we have the silicon design tools, which need to be floor planned appropriately, looking at the die floor planning in conjunction with the package design, where we look at things like package form factor, package layer count, all of the design rules across the silicon and package design tools. We work on the package designers should work very closely with the silicon design team to optimize the floor plan and the metal layers in the silicon design to give the right bump pattern optimization to enable the most efficient package and silicon design. And then on the other side of things, on the package side, the package designers work very closely with the board design teams to take a look at the board database, make sure that the BGA footprint or the LGA footprint is appropriately designed to, again, hit the right board layer count, board form factors, board connectivities, and optimize the performance across the entire stack. Typically, we have not done this, and I think the tools are well in development, but there's still a lot of work to be done across the multi-domain design planning, which is planning the design upfront from the silicon package and board, and then of course the multi-physics analysis across thermal impact of the whole stack, the mechanical impact, and the electrical analysis. So the key thing that we are looking at is to maximize the benefits of the technology, to make sure that we are not individually optimizing each of the vectors, but do a full co-optimization. Trade-offs are critical, and we do not today have fully developed tools to do an optimum trade-off analysis in the EDA ecosystem. And that's something that we have been working on with, and I have a couple of slides on that, with the EDA vendors to make sure that we get our inputs in to drive the right EDA ecosystem. I thought there was a question or a comment on the bridge.
There wasn't, but I just want to ask. I mean, so that's the ideal state. Is there anything today where, let's say, a board designer makes a change that the silicon designer sees in your tool flow, or is it iterative? You have to sync each of these systems today. Is it fully interconnected?
It is not an auto sync. But yes, we do have a system, and I'll talk to that in a few slides, is where the board and designer talks to both the package designer and the silicon designer, and the data flows seamlessly across the three tools. But if the question is whether the silicon designer automatically makes a change based on the board design, I don't think we are quite there yet.
Got it.
The design optimization, obviously, like we talked about, includes the architecture selection, the fit, routability, signal integrity, power delivery, thermals, and mechanical design analysis. So we have a lot of things. In the past, we had a very hierarchical flow, one directional flow. You start with the silicon design, go to the package design, go to the board design, and now with both the interposer in the middle or the EMIB in this case, it is a very iterative process where we have the physical design going on simultaneously across all of the domains, as well as analysis and electrical analysis going, and electrical, thermal, and mechanical analysis going on simultaneously with the design to essentially co-optimize what we would call the STCO, the system technology co-optimization ongoing. So for the package design complexity, obviously stresses the EDA tools. I mean, with these bump pitches shrinking rapidly, with a lot of chiplets coming into play into one single package, the databases become very large. We have a high aspect ratio of the features from silicon to package sizes. There's a lot of different data formats. There are a lot of formats out there. We have the internal silicon, external silicon or foundry silicon, bridge dies, multiple different technologies in package substrates, looking at different data formats. So this presents another challenge to make sure that all of the data formats can be seamlessly read into a central tool where we can look at least do the visualization and the planning properly. Silicon package co-design, and it's actually silicon package board co-design, is interactive and bidirectional, and that obviously again stresses the EDA tools to make sure that we can export across different tools into standard formats, CAD agnostic formats, so that we can all the participants in this effort would be able to look at the data seamlessly. And obviously we need newer tools, and we need a revolutionary scaling up of the tools is needed, which is something that we are working very closely with the EDA vendors to essentially enable. So what do we mean? I mean, we hear a lot of people talk about STCO and why it is important. And for us, STCO is the optimization of the entire system. It's a co-design optimization where we take the silicon design, the top metal layers, the MIM layout, the bumps, use the advanced design rules, work with the package design optimization, which would be the bump map, the layer counts, the form factor, the power delivery network, signal integrity, use our advanced design rules to correct the right ball map and the yield. And then obviously the same thing then goes to the board where they look at the ball map. They'll optimize the ball map such that we get the right layer count, the right power delivery network, the signal integrity, and so on and so forth. For us, power delivery and signal integrity becomes very important, especially because now, especially on the power delivery, you are using elements from all of the components, from the silicon, from the package, and the board to create a coherent power delivery network. And you're not just stitching power delivery elements across the silicon package and board. In essence, it requires what we would call is a full co-optimization methodology to get the right performance vectors. And I've added software in there. I'm not a software person, but obviously this whole thing, pardon me, has to work seamlessly with the software system that it's being designed for. This is a picture that you had seen on the last slide. I just want to show it in a larger. It used to be that the thermal mechanical trade-offs were very, very serial. And what we have worked on is essentially the package design database can see the silicon database, at least for the top metal layers and the bump layers, and can propose changes, additions, edits to that directly in the database, which is fed back to the silicon design team, who then assess the changes and come back with whether the change is possible, not possible, what is the impact, but it is done seamlessly. It's not like somebody has to sit down and talk to and tell them make this change. It allows the package designer to actually make some of the changes into the database as proposed changes, annotate them accordingly, and then feed that back to the silicon team, who can read it in their tools, and if the change is agreeable, make the necessary changes. So we do a lot of work around how do we optimize the IP layout, how do we put the bumps there, where is the way, which is the right location for the IP placement, what is the whole floor plan going to look like, how are we going to break out all of the different power domains, how are we going to break out all the signals, both for die to die, etc. We do the analysis concurrently with the silicon design team. So the serial flow is not, I mean, there is still some level of serialism in the system, but at least at the top metal layers, once the silicon database is getting ready, the package engages very heavily, and the board team engages very heavily through the package design team to make sure that the way the silicon is spread out to the balls, all of the signals and power domains are appropriate for the board design that is being considered. So I think the message that I'm trying to give is that the serial way of designing is really not going to work in a 3D or in a 2.5D packaging environment. We need to have a very coherent strategy for doing a full system co-optimization, else we will be leaving efficiency vectors on the table and not be able to drive to the most optimum solution. We have been working with Siemens XSI, which is a co-design tool, which essentially allows us to look at all of the different vectors that we have talked about in one environment. It is a co-design planning and visualization tool, which essentially aggregates all of the data that we are getting from different sources and formats into a cohesive system model for planning. We define connectivities in context of the full system. You can see these pictures, which essentially have the same message. You're optimizing across the die, interposer, package, and the board. Maintains the full system net list, and then it allows us to then take, and we're developing tools which allows us to take these into our physics tools, which would be for the electrical, thermal, and mechanical modeling, which would then be able to feed the data back to the design team if there are any concerns, issues with the way the layout is proceeding. And obviously, in the past, and I think we still there in some places, it reduces all of the dependency on having manual spreadsheets, emails, communications, etc. It reduces iterations that we have to do because you look at the whole picture holistically, and it is not that the board designer comes at the end and says, oh, this ball map will not work. You need to make these changes. It drives, of course, better IO assignment. You can visualize things better, and it allows the design engineers to get a much clearer picture of the whole stack. and it is very scalable. We have actually pushed it up to handling, it says 500K plus pins. We are handling a lot higher pin counts than that now. So XSI is a co-design tool that Intel has been collaborating with Siemens to develop and use, and that's one of the tools that we are using. We are collaborating with all the other vendors also to develop and make sure that all of the data planning and all of the tools that we use for design are fairly CAD agnostic and not dependent on any particular tool. So as we talked about, the EDA ecosystem enabling is critical to delivering the best-in-class tools for Intel and industry overall. Like I said, we are partnered with XSI was one of the examples where we are partnering with all the major EDA vendors to drive the STCO perspective with the rest of the industry. We have worked with ANSYS and Siemens to deliver a fully coherent power delivery methodology for 3D IC, which comprehends the power delivery across the network, across the board, the package, and silicon to deliver the best PDN solution possible. We are working with all of the vendors to deliver a cloud-based design enabling, which is today in flight, and obviously will require significant effort from the industry and from all of the major EDA vendors, the three major EDA vendors, to drive this 3D IC STCO capabilities for both the package and PCB.
So Sujit, a question is where does test come in? Does test access the same database, or does it have to get extracted out for test?
Today, it is getting extracted out for test, but we are working with our test team to make the data flow again seamless in the sense that it would still be some level of extraction from the database, but what it would do is it would make it seamless that the data is formatted into the test readable format automatically.
Yeah. And is this database, let's say, is it proprietary to the tool vendors, or is it a neutral sort of format that you can write additional tools to interface?
We are looking to make it neutral and make it agnostic to the CAD tool being used, so that it would be, for example, I would use LeftDef as an example for moving stuff from silicon design databases to package databases. The tools may have some proprietary algorithms to read the databases, but the databases move between different tools seamlessly is the goal. Which is exactly, Ira, you hit the third bullet, which is we need a standards-based EDA ecosystem to achieve the co-optimization, that it should not become tied to a particular vendor, but that the databases can be exported from each of these EDA tools in a neutral format, which could be read by some other tool.
But actually, to interrupt there, I mean, you really don't want to export. You just want to be able to access the data, so you don't have to go through a step to export it.
Correct, but I think right now, I thought your question was, right now we export it into a format which is read it, but at the end, yes, which is what the seamlessness comes into, is that you access the data as opposed to exporting the data. Absolutely.
Thank you.
So just to close it out, I mean, we do believe that the silicon package code design and analysis should be standardized and proliferated across the industry. This gives us an opportunity, obviously, to partition and work our specs for the system optimally across all system ingredients. I didn't talk too much about it, but one of the key things that always becomes a contention is how do I partition the performance budget, for example, an insertion loss budget across all elements that go into the final system. And what this allows us to do is run a number of scenarios fairly easily to be able to come up with the best possible partitioning of the budget across all of the system ingredients, so that we can meet the total performance and cost target for the entire system. And of course, as I had asked and as we had mentioned, we do need a standards-based EDA ecosystem to achieve this co-optimization across the system, across all chiplet foundries and the foundry ecosystem. That's what I had for today. Hope you guys had got something out of this, and if any other questions.
Yeah, there's a few. So one of the questions is, how does this STCO methodology change when you have you're supporting multiple applications with the same piece of silicon, the same chiplet? I mean, so can you have one chiplet and then co-design 3 different end products at once, or you had to take 3 different copies of the chiplet? And I mean, so example, if you make a product with high IO or high GT or high compute, you know, how do you get your feedback as you're designing the chiplet, for example?
Correct. So the way one can envisage this happening is that you have really broken it down to the really simplest level ingredients for the system, and each one of them is different. So you could take, for example, you could require SerDes at a certain speed, but your compute die remains the same. So you could have the same compute die talk to different SerDes styles which run at different speeds, so that you get a different system level performance at a different cost point. Or you could take a bunch of different core tiles and you can obviously stitch them together to make one really, really gigantic high core count system, versus taking the same chiplets, cutting it out and using half of them only in a cheaper design, cheaper package to make a low performance but a lower cost product for a different segment of the market.
I understood that that's the approach to chiplets. The question is, can you be co-designing the chiplet itself with the 3, let's say 2 or 3 end applications in this paradigm of STCO, or is the chiplet frozen?
Ira, you broke off with the, sorry, Ira.
Okay. No problem.
Ira, I don't know if it was just me or it was you, but you did break up in the middle and I couldn't make out your question.
Okay, so let me try again. Hopefully you're hearing me.
Now I'm hearing you.
Okay, so the question is, oh, sorry. I understood that that's the approach of how to reuse a chiplet or use a chiplet in multiple places. But could you be co-designing the chiplet? Let's say you have 3 different product teams working on 3 different end applications. Could they be pulling from the same design database for the chiplet and all proposing changes? Or does the chiplet need to be frozen to do what you just talked about?
Broke up again, but no, the chiplet does not need to be frozen. I think I got your question, Ira, just to let you know, though you did break up a little bit in the middle, but I think I got your question. The silicon design teams there can be 3 different silicon design teams doing the same thing on the chiplet, where they would emphasize different parts. So that's where all of the IP pieces start coming into play, where you would use the different IP pieces to do that. But yes, that is exactly how it should be done also, because that also minimizes the load on the number of silicon design teams that you would need to design every piece of silicon.
Sujit, thank you very much for an excellent presentation and really insight into the challenges of doing what I'll call full stack co-design, because there are a lot of different players to get the design right. So thank you very much, Sujit. I want to once again thank our sponsors, Advantest and ASE Group. Advantest receiving the highest customer ratings in the annual VLSI Research Customer Satisfaction Survey for 2 consecutive years. And ASE Group, the chiplet era has begun and helping drive the solutions in packaging and test to deliver these advanced packaging technology to make heterogeneous integration a reality. So I thank both the sponsors for making the event possible and free of charge to everyone. And I most importantly thank all of you for spending the time with us. Hopefully you've enjoyed the presentations, and I'd like to thank the presenters once again and wish everybody a good day. Thank you.